All right, I'd like to welcome you to the presentation of the highly automated driving function and the motion controller. So this presentation will be twofold. The first part will be about the highly automated driving function, and the second part will be about the motion controller, which is a different unit. So first of all, the highly automated driving function is implemented as a lightweight function based on the intelligent driver model, where multiple adaptations were made by us to improve the behavior of the vehicle. It is implemented in a distributed way in ROS, a robot operating system, and then we have a conversion layer from OSI messages into equivalent ROS messages. We have the diagram here, how the function is built. So we have three kinds of input. We have a driving goal in terms of a motion command. We have sensor information via OSI sensor data, which is in form of object lists, and then we have odometry in form of host vehicle data. And we have separate modules. We have a routing module, we have a sensor fusion module, we have a localization. The sensor information is fused into one object list, which is then used for object tracking. And then we have object filtering to filter out the most relevant objects. And all information then is used by trajectory planning to create an output trajectory, which is then sent to motion command. So we have different features in the highly automated driving function. We have multi-sensor support with an object tracking for occluded obstacles. We have reaction to road users according to their classes, but also to the relations with regard to the ego vehicle and also lanes they're on. We have a right-of-way logic, and we have traffic light logic. Down here we have an image of the scenario of the right turn scenario of milestone 1 and 2. So for the integration of the whole function, we have a system where the highly automated driving function itself is run in a Docker environment. So this is all the ROS nodes visualized here. And we use the OSMP network proxy to integrate the function into the simulation core. So the driving function itself is not an FMU, but the proxy is. And then the communication is done via TCP. Then there's a conversion layer in the networking node to convert from OSI messages to ROS messages and trigger all the internal communication. This system has several advantages. So we have, first of all, and most importantly, a platform-independent integration. So the driving function is exclusively run in Ubuntu, but we can also run the whole system with the Docker on Windows, for example, which is often used. We have an out-of-the-box support for distributed computing, so we can run the Docker on a different system to save resources or speed up the simulation. We still have the full easy modular integration as an FMU because the proxy serves as such. We have full OSI compliance, and we have a showcase here that we can use arbitrary common frameworks such as ROS is in a Docker and have a prototype architecture for those. So for the motion controller is implemented as a different, separate as FMU. There's two advantages with those. First of all, we are able to run different simulation rates between the motion controller and the highly automated driving function. And also we are easily able to exchange different kinds of motion controllers because they often have to be adapted to the vehicle model. So this is the second advantage. The motion controller, as I said, is specifically designed for the vehicle model in use in set level, which is also presented in another B1-7 marketplace. It is a nonlinear state space controller, which takes the nonlinearities of the vehicle system into account. The kinematic quantities that are controlled are acceleration and curvature. And then the actuator management, which is a separate module, is then taking care of translating those into actuator actions. So finally, we have a graph of how the motion controller is built up. So on the left-hand side, we have the motion planning, which is then sending the trajectory into the motion controller. We have a basic controller at the bottom, We have then two steps for nonlinearities and pre-control, and then finally we send out the acceleration and curvature to the vehicle dynamics module, which then has the actuator management and the actual simulated actuators, which then feed back the actual state of the vehicle, including the position of the vehicle as feedback for the controller. So thank you for your attention. Yeah.